Today, I'm excited to introduce our project of West Kowloon Station, Hong Kong partial pier foundation works. Uh, these are our group members. Uh, we will introduce this project in four parts. The first part is introduction, literature review, and the WBS structure. The second part is construction program. The third part is cost estimations and project control. And the fourth part is optimization. Mm, a key component of the Hong Kong section of the Guangzhou-Shenzhen-Hong Kong Express Rail Link. This massive infrastructure project covers an area of approximately 120,000 square meters and includes four basement levels, all suited on reclaimed land with highly complex geology. The site presents significant geotechnical challenges, including deep soft soil, variable rock strata, uneven foundation bearing capacity, and groundwater control. These conditions demand robust foundation and retaining structures to ensure long-term stability and safety. To fit the scope of our course project, we have narrowed the focus to an experimental sub-project that retains key technical process and representative structures. This allows us to conduct systematic analysis and optimization while staying true to the real-world context. Our literature review highlights the importance of cost estimation and control in large infrastructure projects. Factors such as material type and quantity heavily influence the budget, which in our case is estimated at around 150 million. Accurate engineering measurement is also critical. For example, large diameter board piles are measured by theoretical net length, and underground continuous walls by design net volume. We also refer to relevant references such as pile design and construction practice by Tomlinson and Woodward as the basis for our selection parameters. Now let's look how we have structured the work. The project is divided into five main phases: design and planning, pier foundation construction, quality control and monitoring, safety, environmental and management, and risk management. Each phase is broken down into detailed tasks to ensure through execution and accountability.
Hello, I'm Liu Hanyu. The overall project is scheduled to start from December 1st, 2025. The concludes on October 22nd, 2026. This spans a total of approximately 234 working days, effectively fitting within the stipulated 12-month period. Here is the project work schedule. Task durations were estimated based on a combination of historical data from similar heavy civil projects in Hong Kong, industry standards, productivity rates, and the specific scope of the reduced scale works. For instance, the 16-day duration for excavating inside of casting was derived by considering the total volume of excavation for the certain reduced scaled board piles and the average daily process rate of a modern rotary ridge in challenging ground conditions. Producers' relationships were defined to reflect technical and logical dependencies. For example, the prepared soil investigation report task naturally depend on the completion of soil sampling, while the start of pre-drilling on site is contingent upon the completion of both construction drawings and the technical plan, ensuring that construction begins only with fully vetted and approved documentation. The allocation of resources and the assignment of responsibilities were guided by the specific expertise required for each task. Specialized activities such as soil sampling and proof drilling were assigned to specialized geotechnical subcontractors, leveraging their specific equipment and skilled technicians. Major mechanical resources such as rotoring rigs, cranes, and concrete tracks were matched to tasks based on functionally necessary and operationally efficient. This careful matching ensures that each work package is executed by qualified personnel using the concrete equipment, thereby maintaining high standards of quality, safety, and productivity. This, uh, this is the AON diagram, and this is the project's Gantt chart. We can quickly understand the project schedule by this chart. Now, the most important part, the critical path. The tasks on the critical path are the extended duration activities within the board pie installation sequence. These tasks have zero float. Any delay in them will directly delay the final project completion. The planning is considered rational and robust because it actually reflects the technical dependencies of a foundation project. This approach ensures that essential compliance and monitoring functions are maintained while focusing management attention on the critical activities that directly govern the project timeline, thereby optimizing the likelihood of on-time and on-budget completion.
Okay, I'm Gao Mingjie. I will continue to introduce the cost estimation and the project control part. So this part, I choose the excavating the inside of casing as a task from the pile foundation section to present an example and the way through this explanation for other tasks. According to RLB company's cost report, we can use this cost data as a reference. We use medium number 13,500 as the unit cost of per meter bore shaft. And we made some assumptions, 8 hours of work per day, 5 days per week, and the task continues 20 days, which is 160 hours. Drilling speed is 2 meters per day, and the cost of a single bore pile is shown on the slide. Also, we made some assumptions to calculate ownership cost and operating cost. So under these calculations, we got ownership cost, repair cost, and tire replacement cost, and fuel costs. Finally, the total cost times 30 piles is 114,511,052.1. The drilling cost calculated by the two methods show significant differences, and the cost reported by RLB is based on the total contract price for large-scale projects from like economics of scale, while the ownership and operation cost method only calculates the ongoing expenses for the daily operation of the equipment and does not include one-time large investments. Therefore, the latter result is lower. For project control, these are the formula for earned value management. Based on the shaft volume part, each task is divided into two aspects, planned and actual completion percentage. It shows how much work was supposed to be completed by a certain date and compared it with the actual complete amount to obtain the basic comparison chart.
By project completion at week 20, the actual cost reached higher compared to the planned budget, representing a cost overrun of 243,641, which is 6.38 percentage over budget. About ASCO analysis, from week 7 through 14, significant gaps emerged between PV and EV. AC curve consistently diverged above the EV curve from week 7 onward, demonstrating that the project was incurring higher costs for work performed than originally planned. Activity level analysis identified the shaft volume activity with 50% weight as a primary contributor to schedule delays, achieving only 80% completion by week 11 compared to the planned 100%. The consistent pattern of both CPI and SPI remaining below 1.0 through most of the project durations indicates integrated performance issues rather than simple trade-off between cost and schedule. The final CPI of approximately 0.94 confirms persistent cost inefficiency throughout the project lifecycle.
I'm Zheng Xishuo. Next, I will share the optimization plan for the Board's Pile Foundation project at Hong Kong West Kowloon Station. First, let's talk about the project core pain points. We needed to build 30 board piles with a limited time and budget. Two major issues stood out: high costs and severe risks, which could wipe out the contingency reserve. Our goals cut core risks to below 5%, save at least 10 million in Hong Kong dollar, and stick to the 20-week core construction window. For resource reallocation, we split the process into 5 steps, where work breakdown structure and crucial path method. Staggering non-crucial tasks to hit 71% utilization for the main rig and 91 for the fleet. For risk preemption, we used FMEA 0.6 million in Hong Kong dollar. Standby rig allows 1-day swaps for failures, and camping drilling speeds at 2 meters per day reduce collapse risk from the resource. On safety management, we created a 13-day beam-based modular training program costing 0.72 million in Hong Kong dollar and boosting hazard recognition speeds by 40%. For equipment inspection, we streamlined checklist for 180 to 60 items and set up a two-tier control loop, daily operator self-checks, and mostly third-party audits tied to the PDCA cycle. Finally, the results. In cost, we save about 11.35 million in Hong Kong dollar, and in schedule, about 30 piles finished in month 7, and avoiding a potential 150-day overrun. And in safety, 0 recordable incidents and far better than the industry average of 2.3 per 100 piles. And the optimization package is now a reusable playbook for the similar projects. That's all. Thank you.